Okay, so we're going to get started here on chapter 7. And I don't know if the video works at all. Start here. Okay, so chapter 7, this is about roadway design. And again, this is about the nominal safety. And nominal safety basically means that you're looking at the design standard, you're looking at a manual, and using that manual then to figure out what type of radius I need to provide on this curve that I'm trying to design. How do I change direction between, for the roadway, or how do we provide transition between different grades, an upgrade and downgrade, for example. So that's what, chapter 7 is about. And let's see. So this is sort of your challenge of highway design. For now, the challenge of highway design is looking at how do I fit the existing terrain on a roadway while maintaining design standard for safety and performance, right? So you're looking at, like, let's say you're think about Cuesta grade, for example, right? So Cuesta grade, it's a pretty steep upgrade, and then you go and get on the other side, then you have a little bit of a downgrade to go there. Now you will see that that's basically a top, hill there, right? So you're essentially navigating that hill to get around the hill on the other side of that road. So you can't quite overcome the topography of an area. So what you try to do is, like, what's the best way to provide that transition between going up the hill and then coming down the hill on the other side, and make sure that the drivers are comfortable as they're navigating that environment. And to do that, what we do is, like, we fit some conventional curve into irregular terrains, because the natural terrain is what it is, right? It's not governed by parabolic equations or anything like that. It is what it is. But then when we're building the roadway, we want to kind of come up with some good design that provides comfortable rides to people to go from one side of the highway, on one side of the hill to the other side, and so forth. And same thing about, sometimes you might have to just change directions because of because of a river, because of a lake, because of a mountain, whatever it is, right? So sometimes it's going up or down, so like a vertical change in direct, or vertical change in elevation, and sometimes it's change of direction, right? Whatever you're doing, you need to do those things on these roadways. So what we do is, like, we do some. So this requires you to know some geometric design, some geometry, basic geometry, some trigonometry, and kind of use those information then to come up with some set of coordinates where the roads will pass through. And then we ultimately do that using the AutoCAD Civil 3D. So you will have a CE 322 lab that you're going to do to kind of, maybe you've already done it if you've taken that class, or maybe you're taking it right now. But you are going to learn about how do we lay out a road at a certain location, and then we try to minimize cut and fill. So those portions you're going to learn in the lab. How do we minimize cut and fill on the roadway? But for now, I think in this class, in the lecture portion of the class, we are going to learn about, how to design vertical curves, how to design horizontal curves. So these, and what shape do they take? And, and then make sure that, we are providing adequate side distance on all of those curves that we are designing. Okay. So that's the purpose of this class, or this lecture here. So the elements of design that we are going to learn. So there are actually 3 different elements of the design. One is vertical alignment. So where the road passes through vertically, so going up or down. So vertical alignment basically governs, how do we do the elevation transition, basically, the upgrades and downgrades. So that's your vertical alignment. And then if there is change in grade, like going from upgrade to a downgrade, or going from a 6% upgrade to a 2% upgrade, those things have to be connected via a vertical curve, right? Because, what happens is that you cannot have a roadway that looks like this, right? So for example, if you're designing a curve, you cannot have, let me draw a line here. So you have a road like that. Let's say this is 6% grade, and then you have, starting from here, you have a 2% grade. You cannot have a point like this on your roadway, right? You're never going to have a point like this on your roadway, because that won't be possible for the drivers to navigate. So what we do is we try to connect these grades using what we call the vertical curve. right? So not this, but let's see if I can get the shape to be just plain drawing. So we try to connect these with smoother curves so that the transition from one upgrade to another upgrade is smooth. And the same idea applies if you're trying to do transition between upgrade and a downgrade, right? What we want to do is we cannot have a roadway like this, right? Or we cannot have a roadway like, like this either, right? We cannot have these. So what we try to do in vertical alignment is that we make sure that we are providing appropriate transition from upgrade to downgrade using vertical curves like this. Okay, and then same thing on the downgrade side. They're hard to do on a computer screen, but so you're trying to do like these transitions so that the change of grade from upgrade to downgrade is smooth in nature, right? So it's not like, discontinuous from one point of the curve to the other. Okay, and then obviously we want to make sure that there is side distance, adequate side distance is available. If you're traveling on a grade like this, right? If you're traveling on grade like this, you may have seen the sign, something like that says hill blocks view. I don't know if you've seen some signs like that, hill blocks view. What does that mean? That means that you have a curve like this, you have a hill type of situation, and the curve that's designed, if you go too fast on it, you're probably not going to be able to see something that's happening on the other side of that curve and be able to stop for that hazard, if there is one hazard available there, or if there is a hazard coming up there, right? So in those scenarios, you want drivers to slow down, or you want to design your curve in a way that the drivers can see adequate distance. And we are going to learn to do all of that in your horizontal alignment. I mean, in your vertical alignment, I'm sorry. So you're going to provide that side distance. Now, when we talk about vertical alignments, what we are looking for, or what we are looking at, is what we call the profile view. Okay, so we are looking at the profile view when we are talking about, when you're talking about vertical alignment, we're looking at the profile view. So this is what we call. So anytime you see me working on a vertical alignment problem, you should immediately know that what I'm drawing is a profile view. Okay, so I'm looking at the roadway, from the side, right? I'm looking at it from the side, looking at roadway going up or down. So this is the profile view that we're interested in. Now, when you're doing horizontal alignment, when I'm talking about horizontal alignment, that means I'm talking about a change in direction. Now, I have to say, when I'm going to draw it on the board or on the screen here, what you're going to see is that I have, the picture that I'm going to draw for vertical curves and the picture I'm going to draw for horizontal curves, they're going to look very similar. But you have to remember, when I'm solving a vertical alignment problem, I'm drawing what I call the profile view. But when I'm solving horizontal alignment problem, I'm looking at the top view. Okay, I'm looking at it from the top, and it's talking about the change of direction. And this is a very important distinction when we talk about the length of the curve and all of that. So I'll keep coming back to it. Anytime I'm solving a problem, I'll make sure that you guys remember that I'm drawing a profile view if it's a vertical curve problem, and it's a top view if I'm looking at it from or looking at a problem that's about horizontal alignment. So the horizontal alignment is all about change in direction. So I'll still have like say my roadway is going this way, but I want my destination is over here, for example. If my destination is over here, so then I'm going to have a change in direction like this, right? So how do I connect this now? How do I connect these two roadways? Now, it's perfectly fine in some cases to have the roadway go all the way here and then have the drivers make a 90-degree turn, right? Sometimes that does happen. Sometimes we have these T intersections where we sort of have that, right? But in a lot of cases, to provide a more efficient movement of vehicles, you might have to actually connect these two directions of roadway using what we call a horizontal curve that looks something like this. Now, so this view, if I'm looking at it, this view for horizontal alignment, I'm always looking at what I call a top view. Okay, so I'm looking at it as if I'm a bird looking down on the roadway alignment. Okay, now the key difference that you're going to see, and we'll talk about that when we do the vertical alignment, the design of the curve that we're talking about, these curves, these are parabolic curves. So the curve that we draw on with profile views, they're parabolic curve. But when we talk about these horizontal alignment, mostly what we're going to talk about is circular curve. Okay, so remember that too. So that's another difference is when we're doing vertical alignments, we're looking at profile view from the side, and we are dealing with parabolic curves. And then if you're talking about horizontal alignment, you're talking about change in direction, not change in elevation. You're looking at it from the top. You're talking about change in the roadway movement direction. And what you're designing are circular curves, simple circular curves for this class. I mean, sometimes we have spiral curves. We have other types of curves that we design. But for the purposes of this class, all we are going to be dealing with are the circular curves. If you're interested in designing more types of curves, you will take CE 422. So that's the future class that you can take. If you're interested in more AutoCAD work, more design work, more roadway alignment work, that's your CE 422. Now, in the horizontal alignment, we're not going to dig a lot of details into this. It's because we're not actually going to do the design of what we call super elevation. But when you have horizontal curves, you also need to worry about cross-section of the roadway. Okay, and cross-section of the roadway becomes important when you're talking about super elevation, right? Super elevation is about raising the cross-section of the roadway between the outer end and the inner end of the roadway to provide adequate, force balance for drivers that are driving on that horizontal curve. So anytime we have horizontal curves, we have to also worry about the super elevation, which is an element of, this is the third element, right? So we have to worry about that, and we call it sort of the cross-section design. Again, we don't talk about cross-section design in this class a whole lot. We will talk about what super elevation is, how do we achieve it, how do we do the force balance. So we'll do all of that, but we're not actually going to design a roadway for having appropriate super elevation. And even in your lab, I think you will be given a cross-section. So you're probably not going to do a cross-section design in the lab either, is my understanding, because you're going to be given a cross-section design that you're just going to take and implement into your design and not actually having to do the cross-section design. But it's a very important element as to how do you go from a regular section into a super elevated section. So there are basically three elements to the design. One is vertical alignments, how the road goes up and down as you're moving along the roadway. So that's determined by your profile view. And we design parabolic curves for that. We'll learn to do that. And we'll learn to do side distance analysis for those. Then we'll talk about horizontal alignment, designing circular curves. And we will be looking at top views there. And then when you have circular curves, you have to also worry about the cross-section design, which we're going to talk about what it is and how much super elevation you might need, but we'll not talk about the actual cross-section design. Okay, so we'll study all these three: profile view, cross-section view, and top view in this class, and we'll get started with the vertical design or vertical alignment of the road. Okay, so let's clear this out here. And let's get to the next slide here. So the objective of vertical alignment is to have elevation of highway points. So we want to figure out the elevation of different highway points. Okay, so in AutoCAD, we report it using AutoCAD so that when the construction crew or the actual people who are going to build that road know exactly what the elevation has to be. And obviously they will have the survey data, the geodesic survey data with them, so they can do that work in the real world. But typically the role of transportation engineers would be to kind of provide those points as part of the AutoCAD drawing. Okay. The objective of vertical alignment is to determine the elevation of highway points to ensure proper roadway drainage and acceptable level of safety, right? So we want to make sure that, you have proper drainage as well as safety. So we have twin objectives here. And one of the big challenges is when you're transitioning between two grades. How do we transition between an upgrade to a downgrade, or a steeper upgrade to a less steep upgrade, or vice versa, or a downgrade to an upgrade. And that's basically the challenge that we are going to talk about in this class. Okay. And then later on, we'll talk about the side distances on those curves as well, but we'll come to that a little bit later. So we will study two different types of curves. One is crest vertical curve, and the other is sag vertical curve. So let's talk about the crest vertical curves first. In crest vertical curves, we are connecting a G1 grade, it seems like it's an upgrade here, to a negative grade that's G2. Okay, so if you're connecting an upgrade with a downgrade, and you have a curve here, okay, that is what we call the crest vertical curve. Okay, so starting at this point right here, the curve begins and the curve ends at this point. So before the PVC, we call it point of vertical curvature, PVC. Upstream of the PVC, it's a straight line segment, but it's going up. It has a G1, positive grade G1. And then after the PVT, it has a negative grade G2. So this curve is there, this vertical curve, the parabolic curve that I talked about. This parabolic curve is there to provide transition to go from G1 grade, that's upgrade, to a downgrade. So if you think about what is the slope at PVC of that tangent, it's going to be equal to this G1 grade. Okay, what's the slope of the tangent at PVT? It's going to be that G2 grade. Okay, and then the slope will be variable. So if you pick up any other point on this curve, any given point on this curve, like these, the slope will be variable. The slope will change, and the slope will change in a way so that you can achieve that transition in a smooth fashion, and you don't have discontinuity in your roadway design. Does that make sense? What we're trying to do here, we're transitioning from a grade that's upgrade of G1, and then you're transitioning into G2. Now, actually, these crest vertical curves don't always have to be between two upgrades or two downgrades. I mean, between upgrade and a downgrade. You could have a crest vertical curve in any scenario that's this. So anytime G1 value is more than G2 value, you will end up with a crest curve. Right? So if you have a steep curve, that goes from G1 to G2, right? And G1 is more than G2, okay, so G1 is more steep grade, then you will have a crest vertical curve. Yes?
Does still be a parabolic curve?
Yeah, we still design them to be parabolic curve. Yes, so we still design them to be parabolic curve so that we are providing that smooth transition between the two grades. So yeah, always design, unless there is some other geometric challenge, you always design these curves to be parabolic curve. So any transition that we have between grades are parabolic curve. Okay, so you could have a grade like this that I showed you in the previous slide, and let me draw this again. So you have G1, so that's a steeper grade, and G2, it's a less steep grade. So the transition between these two grades will still be a parabolic curve. I mean, it's a parabolic curve, and then it'll be still a crest curve. Okay, and you could have a curve like this where you have a less steep, negative slope curve. So you have G1. Let me do it this way: G1, and then you have G2 is like this, right? So you have G1 less steep and then more steep negative grade curve. What's going to be the transition between these two curves? Is that still going to be crest? Does that still meet G1 versus G1 more than G2 criteria? It does, because the first grade is less negative. This is your transition point. And then the next grade is even further negative. So that design will also be a crest vertical curve. Make sense? Okay. So most numerical problems you're going to be doing in this class, all numerical problem, I can say, they're going to be of this nature where you'll have a positive grade connected with a negative grade. But don't forget, crest curve fit in this definition. Okay, G1 more than G2. Anytime that happens, it's a crest vertical curve. Even the most numerical problems will be connecting a positive grade with a negative grade. Huh? So let's see. So let's see. Let's see. Okay. So now one thing that we do with these crest vertical curves that makes it easier for us to design these curves is that we design them to be what we call equal tangent vertical curves. Equal tangent vertical curves. What do I mean by equal tangent vertical curves is that if you extend these tangents, if you extend the tangent along with PVC like they used to be, and then you do the same thing with PVT like it used to be, and then you figure out their meeting point, okay? The meeting point is exactly going to be in the middle of the two locations, right? So it's going to have equal distance. The horizontal distance between PVC and PVI will be L over 2, and PVT to PVI would also be L over 2. Again, I'm talking about horizontal distance. The other thing is that when we talk about this L value, the horizontal distance between PVC and PVT, we call it the length of the curve. Length of the curve. Now, what that means is that when we say length of the curve in this context of vertical curves, that is the length measured along horizontal plane. Okay, so you're projecting those points onto the horizontal plane, measuring the distance along horizontal plane, and you're calling it the length of the curve. Okay, so we don't actually measure the length of the parabola. That's what I'm trying to get at. So when somebody says length of the vertical curve, you should immediately see that this is the length measured along horizontal plane, not the length of the actual parabolic curve that you're designing. Okay? And the equal tangent vertical curves make sure that the PVC and PVI are L over 2 distance away, and PVI to PVT is also always L over 2. So all curves that we are going to design in this class, most curves that are designed in practice, unless there is some geometric constraint, we design them to be equal tangent vertical curves. So this picture is going to be valid for all crest vertical curves that you're going to work with in this class. Okay, so always the length will be, if we call it L, the PVC to PVI would be L over 2, PVI to PVT would also be L over 2. Okay. Then we define one more criteria. So this G1 and G2, we measure these grades in the units feet per feet. So if you look at the units for G1 and G2, so they are measured in terms of feet per feet, okay, or as percentage. So sometimes they will be measured as feet per feet, or sometimes they will be measured as percentages. So they might say something like, so G1, so somebody might say G1 is 5%. So this is just an example. G1 is 5%. That means that you're going 5 feet horizontal. 5 feet vertical for every 100 feet horizontal. So 5% grade means 5 feet vertical movement for 100 feet horizontal. So if you move 100 feet along horizontal plane, you'll move 5 feet in the vertical direction. So what that means, 5% for this problem would be right here, is that if you draw a line here, that's 100 feet. And again, this is obviously not drawn to scale. So this will be 5. So this number will be 5 right here. And then this horizontal will be 100. Okay, so that's basically what 5% grade means. That makes sense, right? And then same thing, this might be negative 3% or whatever. So that would mean you go down 3 feet vertical for every 100 feet of horizontal distance. So you can measure the grade as feet per feet, which will be 0.05, or you can measure it as percentage 5%. Then we define another criteria, A, capital A, and capital A is the change in grade. So let's say this G2, was negative 3%. Okay, so let's say this G2 was negative 3%. So this capital A defines this capital A value right here. This capital A, that defines how much total change in grade did you achieve when you went from the start of the curve to the end of the curve. So what is this? What do you think is the total change of grade we achieved here in this problem? If we went from +5 to -3, what's the total change in grade? It's an easy question, not a hard question, not a trick question. How much change of grade did you do? Yes, 8%, right? You went from +5 to -3, 8% change. Very easy. Transportation in the classroom is very easy, so you have to always remember that, right? So things are not very complicated. Right? It only gets complicated when people get involved, so that's the only problem. For now, it's pretty easy because we're not designing for any real-world scenario right now. But anyway, so it's 8% change in grade is what you're doing. So in this example, with 5% and 3%, A will be 8%. Or you can say 0.08. And capital A, we define that usually as an absolute value. So you can define that as, so if you want to write down the formula for this, it's going to be absolute value of G2 minus G1. So absolute value of difference between the grade, or you can sometimes write that as, if I write that as absolute value could be also be defined as G2 minus G1. Right, so it's the absolute value of that G2 minus G1 absolute value, right? So sometimes you can represent that with like those two lines are drawn. So that's what it is. Okay, so absolute value of G2 minus G1 is your A value. Okay? L is the length of the curve. Now there is a sort of a corresponding version of this curve. If you go to the next slide, you will see there is a corresponding version of this. There's a corresponding version of this onto the next slide, which is called the sag vertical curve, which is the same thing, but now the condition is that my G1 would be less than G2. So anytime you have G1 less than G2, so anytime you have G1 less than G2, you'll have a sag vertical curve. So in this example, you have G1 value. One less than G2, you have sag vertical curve. G1 less than G2. Now, G1 less than G2 is not about the actual value of G1. So you could have two negative grades here. So if you have a steep vertical curve, for example, if you have a curve like this, very steep, and then you have a less steep G2, right? In this case, G1 is less than G2. Because G1 is more negative than G2, you'll still be designing what we call the sag vertical curve. Okay? Again, most problems that you're going to solve in this class will involve a negative grade connected with a positive grade. Okay? All the other ideas apply. The PVC will have a slope of G1. PVT will have a slope of G2. Right? And this parabola will have a variable slope. Again, you have the same idea, capital A, the rate of change in, the total change in grade. It's an equal tangent vertical curve. So PVC to PVI is going to be L. And then, PVC to PVT will be L. And PVC to PVI will be L over 2. So that's the other thing. PVC is the start point of the curve. PVT is the final point of the curve. And the acronym stands for PVI stands for point of vertical intersection. PVC stands for point of vertical curvature. And then PVT stands for point of vertical tangency. Point of vertical tangency for PVT. And PVC is the initial point of the curve. Okay. So remember these sort of basic definitions of your of your PVC and PVT. And what we'll do to learn in this class is that the basic parabolic equation, it takes the form a plus bx plus cx squared. So in the next class, we're going to learn to apply this equation to do the vertical curve design. Again, this is module 2, so this won't show up in the test on 1 week from today, but this is something that you're gonna work on. So we'll talk about that in the next class. I'm just gonna go ahead and stop here. If you have any questions, please let me know, and I'll try to get your homework graded as well. Thank you.